Welcome to Syzygy, Episode 5, Diamonds from Space. Welcome to another episode of Syzygy. We're back for Episode 5, and this time we're talking diamonds, specifically very, very, very small diamonds, nano-sized diamonds. But here's the best bit, nanodiamonds in meteorites. Diamonds from space. And there's a paper that's been released very, very recently that suggests that nanodiamonds in meteorites, diamonds from space, say something about the origins of our solar system, and in particular, planets that were there that aren't there anymore. Joining me at the microphone, as ever, is Dr Emily Brunsden. Hi, Emily.
Hello, hello.
So, little bit of just test follow-up from last week. In episode 4, we talked about astroseismology, which is your particular kit bag of interesting astronomical tools.
Yep, we definitely need some more on that one day.
We do. We're going to come back for part 2 on that at some point because Emily's not done. There's no way. It's like, come on, I've got all this really cool stuff. But those of you who've been paying attention since we started this podcast know that there's a little satellite up there which is doing its thing, and we're very excited about it. And of course, we're talking about TESS, the Transiting Exoplanet Survey Satellite. Well, it's up. It's there. Going. And I read just this morning that all of the cameras have been tested and it's looking good.
Everything is all systems go.
Fantastic.
It's so exciting.
Go, Tess, go. So we'll be, of course, bringing you updates as we go through this podcast on how that's all going. And as soon as the data starts coming in, Emily's going to start reading that out, point by data point. It's
0, 1, 0, 0, 1.
It's going to be great. You're going to love it. But enough of that. Let's get on to the topic du jour, which is diamonds from outer space. They're not exactly raining down on us, although that's something we might touch on later because I was reading about Neptune and holy cow, but that's a topic for later. Not raining diamonds, but diamonds in meteorites.
Diamonds from the sky.
Diamonds from the sky, that'll do. And yeah, there's been a paper released recently which is talking about a meteorite that landed not actually quite so recently. It landed a while ago, but some more investigation into what's inside it and what it means for the evolution and creation of our solar system. So, Emily, give us an update. What's going on?
Right. Well, first of all, we're going to have to credit the scientists behind this.
That's good.
So this is a team led by Farhang Nabieh, and they're based in Switzerland and from the École Polytechnique Lausanne. Now, they've been working on looking at, in very, very fine detail, the composition of some of these bits of the meteor that have landed on the Earth. So meteors are the things that are burning through the sky, the big fireballs, meteorites, once they hit the ground. So they went and picked up these meteorites and have been studying what they're made of in order to understand the processes and the origins of the meteors themselves.
Right, which is something that astronomers and geologists and astrogeologists, I guess if there's such a thing, would do as a matter of course. If something lands from outer space, dig it up and let's pull it apart and see what's inside it, because that can tell us, well, a heck of a lot. Actually.
Yeah. I mean, it's like free rocks from the sky, right?
Yeah, free rocks from space that tell us about stuff that isn't here on Earth. And, for example, allows us to compare the composition of those rocks from space with composition of rocks on Earth, and you can deduce an enormous amount from that. So this is not a new thing that they're doing, but there is something new in what they've found.
Yeah, so most of the meteorites that we go and pick up, say, in deserts or in Antarctica, they are from usually the asteroid belt. We've got a few from Mars, a few from the moon as well, but mostly from the asteroid belt. And this meteorite is also from the asteroid belt, except the composition of it is really different. In fact, it's got little tiny, tiny diamonds inside of it.
First of all, though, can I stop you for a second? How do they know that it's from the asteroid belt?
So it's to do with the chemical composition. So we've got very good measurements of what the Earth's crust, for example, is made of. You have the iron and silicates and those sorts of elements. And then we know also what Mars is made of. And we know roughly what asteroids should be made of as well, because we find them on the Earth from space.
The asteroid belt is between Mars and Jupiter.
Yes.
And is a fairly wide band of tiny little bits of rock all the way up to quite large chunks of rock, but none of them sort of enough to be sort of planets. They're
No.
chunks of rock which are orbiting in a big band around the sun.
Yeah.
And where's that from?
Well, it's probably a failed planet in its own right. It just didn't have enough gravity. It got disrupted by things like Jupiter. So it kind of pulled it, stopped it forming basically into a nice big round planet. So you just get all the leftover bits that didn't quite get there.
Do any of them have really big sock puppet lizardy things like they had in The Empire Strikes Back? Do you remember that bit from The Empire Strikes Back where Han Solo and Leia, and they fly the Millennium Falcon down into the hole in the asteroid, and there's a big lizardy sock puppet in it that tries to eat them?
Maybe not really.
So disappointing.
But we have sent out space probes, and we have orbited several of these now. So Ceres, for example, which is one of the biggest ones. And yeah, we are still learning a lot about the asteroid belt. There's lots of new things to discover there.
It must be so tempting if you work at NASA to just do a fake video of, and we're showing now the flyby around this. Look out, big sock puppet coming up and eating the probe. I would do that if I worked there. Anyway, so ignoring that, point is you can tell that the meteorite, which has landed, because it's a meteorite, is from the asteroid belt because you can compare the chemical composition, the mineral composition of the rock with other rocks from the asteroid belt, in the same way that you could pick up a rock here on Earth and have a fairly good idea of where it's come from on Earth from its composition.
Yeah.
It's just taking that
It's
a
like a
little
bit
bit
of
further.
a fingerprint.
Yeah. Okay. So it's come from the asteroid belt, and it's got nanodiamonds inside it. So what?
Well, the nanodiamond structures are too big.
Damn. How awful to find a meteorite with diamonds in it that are just too big.
Well, okay, let's give some numbers to this.
Okay, all right.
The nanodiamonds were thought to have originally have been the grand old size of 100 micrometers.
100 micrometers. So a micrometer is a millionth of a meter. So 100 millionths of a meter. That's tiny.
It's very, very
really
small.
small.
Yeah,
Okay.
I wouldn't give it to anyone as an engagement ring.
No, you're going to get some pretty dirty sideways looks if you try that. So don't do that. But these are bigger.
Yeah, and these, well, at least they used to be that big. They're
Okay.
maybe not quite that big at the moment. But from looking at the structures inside the meteorite, we can tell that they probably were this big. And then there's been some other sort of geological processes that have changed the rock structure a little bit since.
Okay, so tiny diamonds, but which were somewhat larger crystals, still not the size that you'd put on a ring, but considerably larger. And that's important because it tells us about the way these things were formed.
Yeah, so you probably know that diamonds, to form a diamond, you need to have intense pressures, and that comes along with intense temperatures as well. So
Right.
you really have to crush things down pretty hard.
Right. I mean,
to get
diamonds, it's just carbon. It's just carbon. It's the same thing as graphite, but you can only form it in these very, very extreme conditions. High pressures, high temperatures. So what are these nanodiamonds or larger diamond structures within this meteorite tell us about where the meteorite came from?
Well, most of the time when we find these nanodiamonds, we think that they're formed by some kind of shock waves that have occurred either, usually a very long time ago in the terms of the meteor's life. So there were some
happened.
collisions and shocks and things that have just sort of temporarily crushed things together.
So it hasn't happened when the meteorites actually hit the ground.
No.
That's not big enough to do that. We're talking more extreme than that.
Yeah.
Okay. So that you said that that's the usual interpretation of where these come from. But this new paper is saying, well, hang on a second. These larger structures suggest something different.
Yeah, they're too big, basically, to have been caused by shock waves.
And you can do experiments. You know, material scientists, people who are into nanodiamonds, can go and see under what conditions you can create these things, over what sizes. And it seems to be that diamond structures of the sizes that they're seeing inside this meteorite couldn't have just been formed by banging some rocks together, big shock waves, that kind of thing, that it must have been as part of something a bit bigger than that. So where are they saying it's come from?
So you need to have enough temperature and enough pressure, And the way to get that is by having basically a big enough thing to have a lot of gravitational force. So if you imagine the Earth, we know that the centre of the Earth is subject to incredible gravitational force from the outer layers. And so we have this liquid kind of irony core.
Right. All the mass of the planet pushing down into the centre creates a central region which is so hot and such high pressure that all sorts of interesting things happen. And so that's what they're claiming these diamond structures must have come from something big squeezing it.
Yeah, and you can work out how big that thing had to be. And it had to be at least the size of Mercury.
Right. So it had to be planet-sized.
Yeah.
So what they've found is a meteorite with the diamonds in it that had to have come from a planet. That's the claim. So, obvious question then, where's the planet now?
What
gone. Happened?
It is long gone.
Right.
So what's really interesting is that when you form a solar system, you understand reasonably well how a solar system forms, although there's still a lot of details that need to be narrowed down. It's not one of the sort of things you can just go out and watch for, a couple of years and see what happens.
I mean, we've got one. We've got a solar system, but we weren't around when it started up. And we've seen a whole bunch of others, as we've talked about, lots of exoplanets out there that we've discovered. But again, we're not watching these things forming in real time. So, all right, let's back up a little bit. How do you make a solar system? Like, where did all the planets come from? In the sort of, we've only got 10 minutes. So give us the condensed version.
The short
of
version.
This. Yeah.
Well, basically, we're the leftover bits that didn't make it into the star. So you've got a big cloud of gas and sort of other materials inside that gas as well, what we call dust. And you basically collapse that down.
And it collapses under its own gravity.
Under its own gravity.
Right. It's got there's a little seed in there somewhere that's a little bit more dense, and that collapses down, and then more stuff collapses around that, and more stuff collapses around that, and eventually you've got enough stuff to make a star.
Yep. And what happens as part of that process is you start spinning.
Right.
And as soon as you start spinning things, you start to create disks. So in kind of a similar way to how you can spin a pizza dough and get a nice big wide disc, once you start spinning material, again, you're going to create this big wide disc.
Okay, so the pizza disc theory of planetary formation. And it's also a little bit like, water going down the plug hole, that as the water comes in towards the plug hole, it spins faster and faster. A little bit of rotation on further away from the plug becomes much faster as you get in closer. So as stuff's collapsing down to make this star, any rotation that was there, even a tiny little bit, becomes a significant amount of rotation by the time it's all collapsed down. Is that the idea?
Yeah. And that forms basically this disk of dust and gas and etc. And then that stuff slowly cools down. I mean, it starts off incredibly hot because there's a lot of friction, there's a lot of energy being released. And then as it cools, you can get little bits starting to stick together. So I'm really going to only talk about the inner solar system.
Sure,
so
fine.
the planets up to Mars.
Okay. We'll talk about the big ones later.
Yeah. So basically you start sticking together. You start with things maybe the size of a bit of dust, you can stick these things together using static forces, get them up to about the size of a grain of sand. Something which we're not very sure of, but then there's this is all bottom up planet formation. So basically you can stick them together until you get to something about the size of a car. Once you've got a car, it's quite easy because you've got gravitational forces to stick other cars to your car or other bits of dust to your car, sized object anyway. And basically it just grows. It's like seeded growth.
Right. And as you said, this is for the rocky planets, right? What they call them, the terrestrial planets, like Mercury, Venus, Earth, Mars, but not the gas giants like Jupiter and Saturn and Neptune and so on. They're a bit different, and we'll worry about that another time. But these are growing just by clumping bits and pieces together in various ways until eventually you get something which is planet-sized.
Yeah, it's got quite a nice name, these kind of proto-sized planets, which are called oligarchs.
Oh, nice.
Yeah.
Nice.
So you get runaway growth, and you actually end up with quite a lot of these oligarchs, many, many more than the 4 that we see in our solar system today. So what's happened to all the other sort of bits that didn't quite make it into these things?
Like when you say many more, like Dozens?
Hundreds probably.
Wow. So the early solar system was a very, very busy place.
It was busy
indeed.
and very violent.
Yeah, there would have been a lot of collisions of big things.
Yes.
Going pow.
Yeah.
You said that the theory about the nanodiamonds and the meteorites previously was that they would have been formed by, big shock wave type pressure conditions, perhaps through collisions in that very early environment.
Yeah.
But this new paper is saying no, it must have come from something even more extreme than that. And the only thing that you could do that with is actually inside a decent-sized planet itself. So it's not just modest-sized rocks bashing together as they circulate around. This is evidence that there had to be a planet.
Mm-hmm. And this is this is a very, very young part of our solar system, long before the planets looked anything like they do now. So, we're looking at something like 10 million years after the first things started forming in our solar system.
And how long ago is that? We're talking several billion years, aren't we?
Yeah, so we're ticking away at about 4.5 billion years for the Earth now.
Right. And you're talking about only a few, maybe 10 million years after that. So we're still talking a lot of billion years ago.
Yeah.
Wow.
Very, very early solar system stuff. So these oligarchs were all kicking around in our solar system. Many of them got flung off because of gravitational interactions. Jupiter does have, quite a significant gravitational effect. It does tend to throw things out a little bit.
So you would have had a bunch of planets just being whipped around and just flung off into interstellar space.
Yep.
Just out there.
They're just gone.
Doing their thing.
Yep. And then, of course, you had collisions as well. So if any two of these objects came too close, then light up, and these things are sort of semi-molten still at this point. So it really is a violent part of the solar system's history.
So from those collisions, you would have ended up with a bunch of stuff, for example, like asteroids in the asteroid belt. But a lot of those bits and pieces would have then subsequently clumped together to make other planets and things like that.
Yeah.
Like the process continues. Things bust apart, join together, and eventually you end up with something which is a little bit more stable, which is what we've got now, which is the inner planets of the solar system with less stuff bashing into them over time.
Yeah. Basically, Mercury, Venus, Earth, and Mars have sort of cleared their orbits, which is actually a definition for a planet now. So they've collected all the remaining stuff that was in their orbital sort of path. And so there's not much left, really, in the inner solar system apart from this asteroid belt.
So is this then the first evidence that we've had for a planet that did exist in the solar system but no longer exists in the solar system? Because that's what they're saying, isn't it?
Yeah.
That we know what all the planets are now. Sorry, Pluto, you're out. But this one says there was a planet. And what did you say it was? Roughly
Mercury could be as big as Mars.
Right. So, non-trivial sized, but is no longer there. And this is evidence that happened. Is that the first time we've got that?
It's not.
Ah.
Now, this one that we're talking about today doesn't have a name.
Right.
Yet.
Which, the meteorite, you mean, or the planet?
The planet.
Right.
Whereas there is a hypothetical planet that did exist early in our solar system, which does have a name.
Oh, okay.
And it was called Theia.
Cool. And where was Theia?
Well, Theia happened to smash into the Earth.
Right. Lucky Theia. Lucky Earth. This was quite a long time ago, I'm guessing, because we would have noticed that.
We would have definitely noticed that. So Theia was about the size of Mars, crashed into the Earth.
Because Mars is what, about a third the size of the Earth? Is that right?
Yeah, but bigger,
Yeah. So, wow. Okay.
Big, yeah.
That's non-trivial. That's, wow.
Just a third the size of the Earth.
So when did that happen?
This happened about 50 million years after the Earth was formed.
Right.
So again,
still very early.
Really early days.
And not many things around to notice at the time.
Definitely nothing there.
Okay.
Earth is still molten-y, melty, rocky stuff at this point. Collisions are happening so often that the surface is really hot still as well.
But not necessarily collisions of that magnitude.
No, those are more rare.
So there must be evidence that happened.
Yeah.
Otherwise, it wouldn't have a name, and this wouldn't be an idea. It's not just someone has come up with this. So what's the evidence that this happened?
Well, we got quite a big piece of evidence, and it's been following us around for 4.5 billion years, and it's the moon.
Right. So the moon is left over from that collision.
Yeah. Yeah.
Wow.
It's amazing. Yeah. So this Theia planet smashed into, probably gave the Earth quite a glancing blow. And all this material was stripped off the surface of the Earth. Maybe the Earth had a kind of a ring at this point from all this material,
Cool.
which sounds quite cool.
Yeah.
Although it would have been a pretty nasty place to live.
Well, yeah. I mean, if you could set up a dome or something and keep all of that out and just look at it, that would have been really cool. But
so we had this big ring of material, which eventually coalesced and reformed into something orbiting the Earth, which is now the Moon.
That's so cool. Isn't it funny how you can know that there is a moon orbiting the Earth your entire life and look up at it and never really consider where it came from? It's just surely always been there and formed with the Earth. But no, that's not how these things work.
Yeah, and it's been relatively recently that we've been able to put this kind of picture of where the moon came from together, because it's only been, in the last 60, 70 years that we've been bringing material back from the moon to actually study, to see, well, what is the moon actually made of?
So does that mean that you can look at rocks from the moon and compare them to rocks on Earth and see the similarities? Is that how you know that they're from ultimately the same, from that collision?
They are almost identical.
Oh, that's so cool.
Yeah, the moon is just almost exactly the same as Earth's crust.
Okay. All right, I am learning something today. That's very, very awesome. Okay, so we have that evidence. The moon is left over from an almighty collision between this other planet. What do you call it? The Theia, and the Earth. We have this new evidence, which is that there was some other planet at some point. I mean, as you say, there were probably quite a few of them, but this is saying, well, at least we know that there was one, because the diamonds in this meteorite couldn't have formed in any other way. And presumably that's what's exciting people about this discovery is but look what we can find in these little chunks of rock that have landed on the Earth. We can have evidence of how solar systems form.
Yeah. And it's not the same planet. We definitely know that, because the timescales are very different and the composition, well, we don't actually have any evidence for what Theia was ever made of. It just seems to have gone. So we definitely think that these are different objects in different times in our solar system.
So we found this particular meteorite, and where was it found, by the way? It was in a desert, wasn't it?
Yeah, it was in Sudan. Yeah.
So how do we go about finding more? I mean, surely then there's an interest in finding more examples of this, because at the moment there's this one meteorite and there's this one paper. Like, that's still, as far as science is concerned, a little bit up in the air, a little bit controversial, because you need more evidence.
Yeah, we can't make a graph yet.
Right.
One data point.
One data point looks good, plausible, but we need more to back that up. So how do we find more evidence?
Well, we can come back to how we found this one, which is really interesting, and then basically use that to go forward and find out how we can find more. So we get these meteors. You'll like this. So the meteor that came in and fragmented into all these little meteorites, it's got a name.
Mm-hmm.
It's got a really good name.
Excellent.
It's called 2008 TC3.
Yep. Okay.
Yeah. Or some people call it Almahata Sitta.
See, that's better.
Yeah.
That's
close to where it happened.
Right.
So this was not an insignificant meteor that came in, right? This was something like 80 tons worth of rock that hit the Earth's atmosphere in 2008.
And how much actually ended up on the ground? Because most of it burns up on the way through, right?
Most of it burns up, yeah. Well, we found 600 pieces of it, which totals to just over 10 kilograms.
10 kilograms from, what did you say? How many
80 tons.
But yeah, that's why these things are shooting stars, right? That's what the big bright trail across the sky is. And only a very small proportion of meteors actually end up becoming meteorites.
Yes.
Right?
Yeah.
The vast majority of it just completely blows up in the atmosphere.
So they shatter apart under the entrance. They go through a huge temperature change, because you think space is really cold. If you're going to burn through the Earth's atmosphere, hurtle through it at incredible speeds. I mean, we've seen rocket launches and how hot the exteriors of those rockets get. So you do that to something that's basically frozen, then the whole thing just sort of explodes because it's heating up so quickly.
Bit of a thermal shock, yeah. But every once in a while you do, if you go out on any given clear night, you will see shooting stars. And those are tiny little bits of rock, or quite big, but blowing apart in the atmosphere. But every once in a while you see YouTube footage from Russia of some amazing meteorite explosion that just lights up the sky. But even then, those are ones that aren't making it down to the ground. The ones that
not
do
many of them,
must have started as a fairly large chunk of stuff to begin with.
Exactly.
So this one found in Sudan, how did they find it? Did people actually see it land?
Yeah, they saw the meteor, and so they could work out roughly the trajectories. Actually, this was a really exciting meteor because it was the very first one that we saw before it hit the Earth.
Oh, right.
And then we're able to find the bits of in the end. So we kind of had that story.
When you say saw before it hit the Earth, do you mean as in while it was still in space or while it was coming through the atmosphere? Go, there it is, quick.
While it was still in space, yeah. About 19 hours before it arrived.
Wow. Well, it's nice to know that if there is an enormous chunk of rock coming towards it, we will spot it. I just, hope that it's not that big that it wipes us all out. But anyway, on this occasion, it was a happy story. Yeah. So they were able to go over there. Quick, go and look for it.
Go look. Now, the problem with going and finding meteors or meteorites even on the ground is that rocks kind of look very similar.
Yeah. I guess, yeah.
I mean,
is it this one? Nope.
I'm sure geologists will disagree.
This one?
But generally, a piece of rock, you can't go out into your garden and pick up something and say, oh, this came from space.
Could the dead giveaway be, yeah, but what about that smouldering bit of rock in the big crater over there? Could you do...
Well, perhaps, but again, they're not really going to create big craters. These things, they're quite small.
Okay, so you're looking for little fragments that haven't, it hasn't hit the ground and made a huge eruption and a crater.
Yeah.
These are little fragments that have scattered over an area that look like rocks.
So, yeah.
Respect to geologists and meteorite hunters.
Well, so therefore you go to places where you don't really expect to find other rocks.
Okay, such as?
Deserts.
And Antarctica.
Antarctica,
right. Yeah. Even so, the deserts of the Sudan area, they're quite big. And Antarctica's quite big. I mean, surely you don't just sort of wander out onto the ice or onto the sand and go, so, anyone found a meteorite? Nope, let's look over here.
Yeah, well, actually we do that,
really?
Especially in Antarctica.
That's a job?
Yeah, although we're not looking necessarily in Antarctica for meteorites that have just landed. I mean, we've been around for a few billion years, our Earth, so it's collected quite a few in the past.
Yeah, I guess that makes sense. So over time, this is getting back to a theme that we have here on the podcast, which is that if you want to do something in astronomy that's quite rare, then you wait a long time or you look at a lot of them.
Yeah.
And in this case, it's been happening for a long time, so there presumably are, it's not like we're tripping over meteorites every day, but there'd be a few of them out there.
Yeah. So that's where we have actually most of our meteorite samples, particularly from the Moon and Mars, etc., have come from Antarctica.
Very cool. I'm still amazed. That's a job.
Yeah.
It's a job, and I'm guessing a hobby as well. There must be a lot of people out there who are meteorite hunters, just scouring the deserts and sifting through snow in order to see what they can find.
Yeah, and then you can put them up on eBay and sell them off to other nerdy astronomers.
Is there a black market for them? There must be.
Well, it's not even black.
It's not even black. It's just. Although I would have thought that if someone does find a pretty decent meteorite, the scientific community, they want that. They want that thing.
If it's big or if it's different, but honestly, there's quite a lot of them out there.
Right. Okay.
Yeah. We do actually have one at Astro Campus that we may have bought off eBay as well.
I need to see that at some point. And if anyone listening wants to bid for a meteorite on eBay in our name and send it to us, that would be a cool way to support the show. I'd definitely support that.
Yeah, so what I guess we're hoping for to find in the future are some more of these meteorites that show evidence for having been in the interiors of early planets.
That would be very cool. Because, I mean, again, many meteorites have been cut up previously and all sorts of interesting things found inside them. But now with something new to look for, a new pointer that says, well, if you find structures like this, that could be from early planetary formation within the solar system, then maybe the hunt's on.
Yeah, we just need more data.
All about the data. And that brings us to the end of another episode of Syzygy. If you've enjoyed the show, as ever, it would really help us if you leave us a review, some stars. As we've established, Emily quite likes stars, so make her day and leave us a stars on a sort of 1 to 5 scale, ideally up the 5 end, on your podcast directory of choice. What we'd also love is if you have a question, or if you've got a comment or anything you want to say to us here on the podcast, then you can send us a message. Emily, how can they get in touch if people want to?
Yeah, really enthusiastic for your questions. So, good way to hit us up is through Twitter. So we're at SyzygyPod, and I can still spell Syzygy, SYZYGY.
Well done.
Did I get it right first time last time?
Actually, you didn't. But I have proof. It's on last podcast. Go and listen to it. I promise you got it wrong.
I don't believe it.
Yeah, no, it's true. But we've also got a website, which is syzygy.fm. So you can go and find us on there, find all the past episodes. And you can contact us through that as well. There's a little form that you can fill out and send us your questions. Coming up next time on the podcast, we're going from the very, very, very small of nanodiamonds to the really quite extraordinarily large. There's been a news story of a discovery of a cluster of 14 galaxies over 12 billion light years away that's telling us something about the very early stages of galaxy formation in the very early universe, which is very, very cool. So join us next time for that one. But otherwise, that's all we've got for this episode. So until next time, we'll see you later. Bye-bye.
See you later.
Your phone's gone off again.
How is that even possible? Look, you can see
it is.
Here.
It's on. I can see it. It's off the hook.
The university needs to look into their phone systems.
All right, go and stop that because we need to wrap this up.